Hey everyone, today we'll be talking about cold form steel studs designed to AISI. So here we can add a new calculation, and under columns we can find cold form steel stud / column. So here we can see that we reference AISI S100-2016 for this design template. And here we list the assumptions we make for this calculator. So we assume that there are no holes in the cross-section. The direct strength method is used for local and distortional buckling. And we assume concentric loading only. So here we can find the geometry inputs. So under designation, you can pick the member type, from furring channel to angle, non-structural stud, a sledger structural stud, track section, U-channel, or Z-purlin. And of course, if there is a section you're looking for but can't find, feel free to reach out to our support team and we'll be happy to make a section request and get that on the template for you. And so here we can set our column height and we can define our unbraced length in each of the two major directions and in the torsional restraints as well. And then the effective length factor. So depending on if your column is pin-pinned, fixed, or fixed free, you can set the effective length factor in each axis manually. So by default, we default these to 1 and we default the unbraced length to the column height. So we assume that there's no bracing. In loads here, we can see that we can enter vertical point loads. So in this case, we have 300 pounds of dead load and 1,000 pounds of live load. And they will be applied at the top of the column. And as noted in the assumptions, we do not consider eccentric loading. So actual eccentricity is locked at 0. And then here we have a toggle for considering reduced companion live load. And we consider this per ASC 716 clause 2.3.1.1. So you can find the description and the reference for that here. And then here we can toggle to include or exclude self-weight. The design criteria we're using for this template is IBC 2018. And we list the load combinations of the loads inputted here in this section here. So we'll automatically consider all the combinations and extract the ultimate actual load. So in this case, it's the 1.2 plus 1.2 dead plus 1.6 live. And then under that, we're considering yielding and global buckling capacity per section E2. So global buckling is the overall capacity of the section of the member, where no deformation of its cross-sectional shape is considered. And then yielding is when the member yields, but no buckling has occurred. Local buckling considers portions of the cross-section buckling or failing. And an example of this would be web crippling. So where only the web cripples and unbuckles and causes failure of the member. Distortional buckling considers movement of the flange in rotation or translation and causes the member to lose stability. And so we'll calculate the capacity here and make a summary table of it here. So this summary table can be found the capacity for local buckling, capacity for distortional buckling, and capacity for global buckling. And these numbers will be compared against the actual demand to find the percentage utilization noted here, and we'll list the governing utilization here. And that's all for this template. As always, if you have any questions, feel free to reach out to help. Thanks for watching.